Imagine dropping a ball. Newton would say Earth's gravity pulls it down. Einstein would add that Earth warps space-time, and the ball rolls into that curve. But what if there's more to gravity than just the geometry of space-time? What if an invisible network of quantum information is also at play, tugging at the ball? In 2024, physicists proposed exactly this, that gravity might not only be a property of geometry, but also a manifestation of information, specifically quantum entanglement. In other words, the universe might have a hidden information fabric woven into the space-time fabric we know. This fascinating idea, called the geometry-information duality, suggests that space-time and quantum information are two sides of the same coin. For over a century, we thought of gravity as bends and warps in a cosmic fabric. But now, imagine that fabric is interwoven with threads of information, quantum threads connecting everything. Could gravity be the shadow of information cast on our universe? Let's explore this bold idea. In Einstein's general relativity, matter and energy tell space-time how to curve, and that curvature is gravity. Picture a trampoline. Place a heavy object on it, and smaller objects roll toward it. That's the geometric view. Gravity without any mysterious force, just the shape of space and time. This theory has been hugely successful. It explains why planets orbit, how GPS satellites work, and even the bending of light by galaxies. But it leaves something out, the quantum world. At tiny scales, particles don't follow the smooth curves of classical space-time. They jitter with uncertainty and entangle with each other. General relativity and quantum mechanics have famously never gotten along. Bridging them is the hardest problem in physics. Enter quantum information theory. This field suggests that entanglement, those spooky correlations between particles, might be key to uniting quantum physics and gravity. Recent ideas hint that space-time itself may be built from quantum entanglement patterns. Imagine removing all entanglement from the universe. Some researchers speculate space-time would just fall apart, as if the threads holding it together were cut. This is a radical shift in perspective. The structure and dynamics of space-time could be deeply intertwined with the flow of quantum information. In short, maybe gravity emerges from information. Gravity, in this new view, isn't just geometry. It's also a product of countless quantum connections knitting the cosmos together. So what is quantum entanglement, and how could it affect something as grand as gravity? Entanglement is a quantum link between particles. If two particles are entangled, measuring one instantly affects the other, no matter how far apart they are. They behave not as two separate objects, but as one system sharing information. It's as if you have two dice that always land on matching numbers, even when separated across the universe. This spooky action at a distance, as Einstein called it, means there's a deep informational connection binding the particles. One way to quantify these ghostly links is through entanglement entropy. This is a fancy term for the amount of quantum information shared between parts of a system. For example, imagine slicing the universe into two regions with an imaginary surface. The entanglement entropy is like the number of quantum threads crossing that surface, linking the two regions. The more entangled they are, the higher the entropy. More information is shared or mixed between them. If there's no entanglement, the entropy is zero. The regions know nothing about each other. Importantly, entanglement entropy isn't random. It often obeys deep laws. In many cases, it's proportional to the area of the dividing surface, not the volume, hinting that information content is somehow tied to the geometric area. This curious fact is at the heart of the holographic principle, the idea that all the information inside a volume of space can be encoded on its surface, like a hologram. Physicist Leonard Susskind famously argued that our universe might be like a hologram, with reality as we know it projected from information on a distant boundary. All these clues, entropy proportional to area, space-time potentially built from entanglement, suggest that information and geometry are deeply connected. Think of space-time as a giant informational web. The threads are entanglement links. Where the web is dense with links, space-time might curve more. Where the web is looser, space-time is flatter. In this analogy, mass energy, like stars or planets, doesn't just curve space by its presence, it also influences the surrounding web of entanglement. Perhaps mass gathers quantum connections around it, and those connections in turn pull on other masses. Gravity could emerge as a kind of feedback between geometry and information. Matter warps the information fabric, and the information fabric tells matter how to move. A recent paper formalizes this vision under the term geometry-information duality. The core idea is simple, yet profound. The curvature of space-time is directly related to the entanglement entropy in quantum states. In other words, for every bump or bend in space-time, a geometric property, there's a corresponding measure of entanglement, an informational property, causing it or accompanying it. Geometry and information become convertible concepts, a bit like how energy and mass are two forms of the same thing. This duality claims that if you know the entanglement structure of quantum fields in an area, you can predict the curvature of space there, and vice versa. To make this precise, the researchers map geometric invariance, fancy math terms describing curvature, to informational measures like entanglement entropy. It's a bit like having a dictionary, translating the language of geometry to the language of quantum information. A flat region of space-time might correspond to low entanglement entropy, while a highly curved region, say near a black hole, corresponds to a high entanglement entropy of quantum fields. This isn't just hand-waving, they derive equations for it. By studying quantum fields in curved space-time, they calculate how much entanglement entropy those fields have across different regions. And lo and behold, those calculations can be related to how space-time is curving. Now, if information, entanglement, contributes to curvature, it should appear in the equations that govern space-time. This brings us to one of the paper's key contributions, introducing an informational stress-energy tensor into Einstein's field equations. That's a mouthful. Let's unpack it. In Einstein's theory, the stress-energy tensor is a bookkeeping device for energy and momentum, from matter, radiation, etc., that tells space-time how to curve. Einstein's equation in simple terms says, curvature equals constant times stress energy. Originally, this stress energy included mass, radiation, and pressure, essentially all classical energy. The new idea is to add another piece to this equation, a term that represents information. The informational stress-energy tensor is a mathematical object constructed from entanglement entropy and its gradients, etc., that acts like a source of gravity. It's as if quantum entanglement itself carries energy, or something analogous to energy, that can bend space-time. So the upgraded Einstein equations now read, curvature equals constant times stress energy of matter plus stress energy of information. In plain language, space-time curvature equals gravity from matter plus gravity from entanglement. This doesn't mean information weighs in the usual sense, but it affects the shape of space-time similarly to how mass energy does. It's a bit like discovering a new kind of charge that gravity responds to, not electric charge, but informational charge.